Hello everyone, welcome to Big Data Thoughts. Today we are going to talk about a topic which many of you have asked me questions on. It is about choosing the right Spark cluster. What should be the size of the cluster? What should be the configuration? So we'll deep dive into how should we determine what should be the size of the Spark cluster. So let's get started. So first of all, what is a Spark cluster? Spark cluster is a collection of computer nodes that are working together to process large scale data using Spark. Now we all know that Spark operates on distributed cluster or distributed architecture. Why? Because we are talking about huge amount of data, and Spark is meant to process big data or huge amount of data. Hence, it is a collection of nodes that are working on huge amount of data in a distributed setup. So it's a very fast general purpose computing framework. And if we talk about, there is a video I've done on the Spark architecture of how it works. I'll put that link. But essentially a Spark cluster is typically, it has one driver and a multiple set of multiple nodes which the driver coordinates with. So the function of the driver is to distribute work around multiple nodes which are acting as worker nodes. So data is distributed across the network, and the tasks are getting executed in parallel in a Spark cluster. Now, there are various ways in which Spark can run. A Spark cluster has different Spark managers that can be used. For example, primarily there are four types of cluster managers. All of these we will look into in detail. But what are these? Standalone mode, Apache, Hadoop Yarn, Mesos, and Kubernetes. People use either of these in various use cases depending on what they want to do. Do they want to do a production workload? Do they want it to be containerized? Do they want to run it in a standalone mode for debugging? Depending on the use case, they use the type of Spark cluster, and that is what we are going to talk about. What should be the configuration, which cluster type should we use. Now, what is the benefit? So benefit of using a Spark cluster, first of all, it is very high performance cluster. Reason being, it uses in memory computer, it is based on distributed architecture, and it is very suitable. Spark is known to be very good with iterative algorithms or real time analytics. So when I say high performance, Spark is high performance because it uses in memory computing that of course speeds up the entire execution. Then scalability. Spark can actually, it is meant for big data world, and it is meant for processing huge amount of data. Hence it can actually process in parallel petabytes of data across thousands of nodes. There is possibility of doing horizontal scaling. So vertical scaling has its own limitation. When we say vertical scaling, it means we are scaling the memory, the compute power of a machine. Now that will always have some upper cap. So it is always beneficial to have a setup or a cluster where you can scale horizontally, which means adding more nodes to the cluster to make it more performant. So Spark cluster has that capability of scaling horizontally. It is fault tolerant. Why? Because the basic building block in Spark, as we know, is an RDD, which is nothing but a resilient distributed data set, and that has the capability of having checkpointing and then having a lineage of how that RDD was built. So it is fault tolerant. In case of failures, it can automatically recover the lost data using that entire lineage and checkpointing that a RDD provides. So in short, Spark clusters are beneficial because they are highly performant, scalable, as well as fault tolerant. And one of the principles of distributed computing is that failures are a norm. It is nothing of an exception. In such a big cluster with this amount of data being processed, failures are normal. So we definitely want a cluster which is fault tolerant and can recover. Failures don't hit it hard. Other benefits are the ease of use, because Spark provides multiple support for multiple languages: Python, Java, Scala, R, all of these. And there are high level APIs, low level APIs are also there. There are high level APIs for complex data processing. Spark is a unified engine. Why do we call it a unified engine? Because it can handle a wide range of tasks, starting from batch to stream to machine learning to SQL querying by using Spark SQL. Now, when I talk about a unified engine, this is important in the context of big data because you may have different kinds of sources, you may have different kinds of workloads. So, it gives you a uniform platform to do that. It can also integrate with lot of other big data tools, like it works very well with HDFS, then it can work with Cassandra, Hive, Edgebase, Kafka, and many others. So it has that integration capability. Resource management flexibility is there because there are cluster managers that are managing the resources like Yarn, Mesos, Kubernetes. They do the resource allocation and management for us. Now we have looked at what is a Spark cluster, the benefits. Let's look at the core functionalities of a Spark cluster. So first of all, the most salient feature is that it is a distributed data processing system. Spark splits the entire data set across multiple nodes in a cluster, and then we can, on each node, we call those nodes as executors or workhorses of the cluster, where they are the ones who are running the actual load. So there are multiple nodes and there are multiple tasks running in parallel. That is why the time taken to process the data is highly reduced. If we do it on a single machine, it is going to take a real long time. Then it also, one of the salient features of Spark is it uses RDDs to manage and process data, and RDDs have a inbuilt lineage and checkpointing facility which makes it fault tolerant. So core principle of Spark is distributed data processing. Then in-memory computation. That is why Spark is so fast, because it keeps the data in memory instead of every time writing it back to the disk, because disk seeks will add to the time. So it does in-memory computation. Overall, it will speed up the entire process, and that's why it is said that Spark is really good with iterative algorithms or iterative processing. Another inbuilt thing is fault tolerance. Spark automatically recovers lost computations. How? By using RDD lineage. So RDD has this inbuilt capability of checkpointing lineage by which you can actually rebuild the lost data. One more feature that attributes to the Spark performance is parallel execution. Since Spark distributes tasks across worker nodes, all the tasks can run in parallel. So there are multiple worker nodes or executors which are controlled by the driver. These worker nodes are working in parallel to execute the job. Each node that is there, it is processing a portion of the data. So it basically, let's say there is a big data set, it is chunked into multiple smaller partitions and it is spread across multiple worker nodes and tasks. That is why the task can run in parallel, and it is very quick and performance efficient. Then there is support for multiple workloads. We spoke about it briefly, that it is a unified engine. Why unified? Because it can do batch processing, which is like our simple ETL jobs in the SQL world. In big data world, they are known as ELT jobs, which means extract, load, transform. So the data is extracted from multiple sources, it is loaded into the file system, and then there is the transformation that happens. We can do stream processing, real-time stream processing, when there are sources which stream data in real time. There we can use Spark streaming. Machine learning, then there can be SQL queries, graph processing. So it is one platform which serves all your different kinds of use cases. Data abstraction. Now what does that mean? So we all know that the basic building block in Spark is RDD, resilient distributed data sets. That's the lowest level of abstraction, and the data is loaded into memory. Now Spark, when I say it provides data abstraction, which means that I don't have to really worry about how internally or at the lowest level the data is getting distributed, the data is getting read into memory and how all that is happening. It is abstracted out from us, and Spark provides high level, low level APIs. So there are three primary data abstractions that are provided by Spark. One, which is RDD, that is the lowest level of abstraction, and we have low level APIs. It gives you better control, but it is easier to use the high level APIs which are provided for data frame and data set. What is a data frame? Data frame, you can think of it logically like a table. It is meant for structured data, which has, so it's like a table which has schema, right? It will have columns, it will have rows. That's how you should envision a data frame. Data set is something which is even higher level, and there are APIs provided for data sets. This typically combines the best of both the worlds, RDDs as well as data frames, with type safety. So three levels of abstraction that we can use: RDDs, data frames, and data sets. It has resource management and integration capabilities, which means that Spark can run on various resource managers or cluster managers, which are standalone, which is built in with Spark, then Yarn, Mesos, or Kubernetes, depending on what we want to use as per our use case. But it does provide this flexibility of having different types of resource or cluster managers. Scalability, of course, because it can horizontally scale. This cluster can scale to a single node to thousands of nodes, and they can operate in parallel. So it is very suitable. It's a distributed architecture and very suitable for handling petabytes of data. Now comes the important question of how do we determine the cluster size based on the data. So there are various ways to look at the cluster and determine the cluster size. One of them is, of course, the data, because looking at the amount of data that we want to process, we have to assess the scale at which Spark cluster needs to operate. So three parameters, which are the three V's of big data, need to be evaluated. We need to look at what is the volume of data we are going to process, what is the velocity of data, as in what is the speed in which we are ingesting the data, and what is the variety of data, whether it is structured, unstructured, semi-structured, what kind of data are we receiving. These three dimensions will affect how we want our initial cluster to be set up, how the cluster should scale. When I say initial setup, the number of nodes, the memory, the CPU, the storage, what should that be, and how will I scale my cluster based on what parameters. So first thing to look upon is my volume, variety, and velocity of the data. That's the first three dimensions. So we'll talk about each, right? Volume, we know volume is nothing but the amount of data that we are trying to process, how many GBs, TBs, petabytes, because if the data is huge, we will require more storage and more distributed processing power. Our worker node should be able to or capable to handle the load, and they should be of good configuration. See, when big data started, when Hadoop came into picture, people always spoke about commodity hardware, which means very cheap and very basic hardware on which Hadoop can operate, because it's not one node, it is a collection of nodes. So even if you have very simple commodity nodes, together they give you the compute and storage that you need. But keep in mind that yes, it can work on commodity nodes or commodity hardware, but in production we generally do not go for commodity hardware. We go for good configuration of the nodes, because our data will increase over time. We shouldn't think only about today. We have to think of the cluster being able to sustain for next 5 years and scale. So we need to look at a good configuration for each node, and together they will give you a very good compute and storage. So volume is one of the dimensions that we have to think about. Then velocity. Why velocity is important? Velocity is what? Velocity is the rate at which the data is getting generated and we are ingesting and processing it. So if the data is of high velocity, which means we are collecting sensor data, real-time logs, or anything which is streaming data into our system, will need stream processing capabilities. So then accordingly the configuration of our nodes will change. Low latency nodes and fast networking should be there to handle this continuous incoming data. We definitely need to auto scale, because with the limited set of nodes with which we start may not be able to sustain. Sometimes for production loads, what we do is we don't scale. Uh, we don't keep the cluster at high capacity always. We know that what is our normal everyday load. Accordingly, we have the cluster. But if we have peak loads, or during certain times we know that we are expecting more load, then we scale up for that time and we scale down. That's the whole beauty of having a cloud setup, because it's extremely easy to scale up and down. So Spark on cloud, whether it is Amazon, Google, Azure, any of it, gives you the flexibility to scale as per your demand. The third thing, variety. We have to think of, even if today we have only structured data, we need to think of what happens if I get unstructured or semi-structured data. The cluster should be configured with those kind of libraries and memory setting which are optimized for handling diverse workloads. It cannot be an afterthought. While designing the cluster, this has to be considered that you will receive different kind of workloads in future. Also, when we talk about this different loads, see, in big data world, it is ELT, like I said, extract, load and then transform. So while loading, we can load any type of data that we want into the same distributed file system. Only while we are processing or transforming it, basically it's a schema on read. Only when I'm reading the data, I need to worry about the schema. Unlike SQL, a SQL server or the SQL technologies, we had a schema which was defined beforehand. It was very a hard constraint saying that this is my table, these are the columns, these are the data types, and everything has to fit into that because it's schema on write. While writing to a SQL system, I am enforcing a schema. But here we have a flexibility of loading anything, any type we want, and we only enforce schema while reading it. So depending on different types of requirements or consumption, we can write our own logic to read the data. So this variety is a very important aspect of big data. So we need to keep in mind while designing the cluster that will it be able to store and process variety of data. So in summary, we should look at these three dimensions: volume, velocity and variety. And what are the questions that we should ask ourselves? We should ask, how much data do I process daily, weekly? And similarly, when I do a daily, weekly projection, I should do a yearly projection and plan, add a buffer to that. If the volume I'm expecting is, let's say, 1 terabyte per month, then the yearly is 12. I would add some buffer to it and say that I need to plan for 15 terabytes. And if it is 3 years, then I have to plan for 45, and then I will scale it accordingly when needed for some time or later on. But that's how we do. We have to do a projection of daily, weekly, yearly with a buffer included. And the impact on the cluster sizes, we will need more storage and compute nodes. For velocity, we should see how fast must the data be ingested. Is it all batch? Is it real time? Is it a mix? Then we have to think about lower latency, in-memory computations, faster CPU. Similarly, for variety, we need to think how many formats and sources do I use. And we have to have more flexible support, processing support, configurations and libraries. Now let's go to the deployment options. What are the deployment options? We have Standalone, we have Yarn, Mesos and Kubernetes. Let's look at each of these in detail. First of all, what is a standalone mode? Standalone is a built-in cluster manager that comes with Spark. It comes by default. It is extremely easy to set up and run, and typically it is used when developers are doing a debugging or they are doing some development where they want to operate in a smaller scale. The aspects of standalone, if we consider three aspects: cost, scalability and control. How does it look like? What are the pros and cons? Cost wise, there is no external resource manager needed. It's low cost because it is built in resource manager. Of course, it lacks advanced resource sharing and may waste resources because it's a very simple resource manager on a standalone machine. So it will not have any advanced resource sharing capabilities. Scalability, it is very simple to scale by adding nodes manually. We can add nodes manually. it is not meant for large dynamic clusters. It is only meant for our development purposes, debugging purposes. We have full control over Spark installation and configuration here since it's a small standalone setup. But it will not allow us to have very fine-grained scheduling on multi-tenant isolation. So that's the con. All in all, it is best for small to medium workloads. For example, dev and test environments, very simple pipelines. You don't want to do a big setup because you're doing a testing, you're doing a small dev experiment, POC. In those cases, standalone mode works really well. So usually very small teams or who want to have a dev test environment, proof of concept, they will go for a standalone because there is a cost attached to having a full-fledged, scaled up, full-blown cluster. Right? It can be set up on-premise also on small VMs using the Spark inbuilt manager. Deployment is extremely simple. We have one master node, multiple worker nodes. The architecture remains the same. It's distributed, one master, multiple workers, but it's extremely simple. We can monitor using the built-in web UI. What we should consider but while doing this is that this cannot be a production setup. This is only for dev test setup. So there is no sophisticated resource management, multi-tenant environment, or scaling is manually. There is no auto scaling. So these should be kept in mind. It is only for having lightweight production. Ideally, I would not recommend production, but if at all you want to do a very lightweight one, proof of concept, some local cluster, or somebody who's a beginner and wants to try on Spark should use this. Okay. The second one that comes is Yarn, yet another resource negotiator. That's the full form of Yarn. So it's Hadoop's native resource manager, and it was very popular in the earlier days of big data. Right now, again, we will look at three aspects. Cost. It is efficient. It is cost effective. It requires a Hadoop setup. Okay. So when Hadoop started in big data world, when Hadoop started catching up, Yarn was the most popular resource manager to work with. Scalability wise, it is designed for large scale clusters, so it is good at resource sharing. But it is a little bit complex to tune it for optimal scalability. It will give you good control over jobs and resources, but less flexibility as compared to Kubernetes and Mesos, which can be used for microservices kind of patterns. So with time, things evolved. Standalone was there, Yarn was there, then came Mesos, Kubernetes to handle more complex workloads, give us better flexibility. So this is better for enterprises which are already using Hadoop or they want to use batch pipeline. So if you already have Hadoop, Yarn is kind of the default choice, and it works well in terms of having production workloads also. So if we want to deploy Spark on Yarn, when should we do that? When we are already having a Hadoop or HDFS setup. It will use dynamic resource allocation to scale executors up and down, unlike standalone, which had to be manual. There are Yarn queues which will isolate jobs, and we can assign priorities of which job to execute first. You can also have Hive and Spark SQL integrated. Right? Now this needs some cons or considerations to keep in mind. This will need a Hadoop infrastructure. It works with Hadoop only. It will require you to fine tune on your own the container sizes, and it is not really ideal for cloud native or containerized workflows. For containerized, we have Kubernetes. So for those workflows, it may not be suitable, but it can very well work for production. So it can work very good for hybrid workload, batch jobs, enterprises which are already having Hadoop. That's where they go for this resource manager. Coming to Mesos. What is Mesos? Mesos is a general purpose cluster manager that can run Spark along with other frameworks. That's the USP of Mesos. It is not just restricted to Spark like Yarn or Standalone. Mesos can run alongside with other frameworks. It is efficient in terms of resource utilization across different workloads. And con is what? More complex setup and less community support. For Mesos, community setup is less as compared to others, and it is complex. Scalability is good. it can work for multi-tenant workloads, and definitely it will require advanced cluster management. The more advanced resource manager we use, we need to be knowing how to configure the cluster. It has fine-grained control. It provides us fine-grained control over CPU and memory. But the usage of Mesos is a little bit restrictive. I just wanted to give you a overview of Mesos so that this name doesn't come as a surprise when there's a discussion about cluster resource managers, but the adoption or usability percentage is lower, so that it's not an active community. It can be used for multi-framework cluster, research labs, advanced hybrid use cases. It scales well. Now it is great for shared infrastructure. Like I said, you can run multiple things along with Mesos. So you can have Spark, Kafka, Elasticsearch all running together. We can configure fine-grained access, coarse-grained access, scheduling, everything can be done. Apache Zookeeper for Mesos master failover. Now Mesos uses internally Zookeeper. It is one of the technologies open source of Apache which is used to manage the failover. The only thing here to consider is the community is not that active, support is declining, so because it's not that widely used, and it is not as actively evolving as Kubernetes. These days you would see a lot of usage of Kubernetes. So it requires a lot of knowledge to operate with Mesos. It is good for advanced users or academic and hybrid use cases. Now coming to Kubernetes. Kubernetes is one of the very widely used cluster manager. It is a modern or container orchestration platform, and Spark supports this integration with Kubernetes. Cost wise, it can be pay as you go. If you go on cloud, like there are Azure Kubernetes services provided, then similarly on Amazon you get that Kubernetes. So these are all pay as you go model because it is operating on cloud, so it is very cost efficient. We can do auto scaling based on rules, and it is very easy. Updates can be easier, container deployment is very easier, so the scalability, maintenance, fault tolerance becomes really easy. But yes, of course, it comes with some cons, like we have to manage the Kubernetes cluster. It requires certain amount of extra setup, networking, monitoring. But otherwise, it has high control, container level configs can be done, security versioning can be done. The only thing is it has a steeper learning curve because it is a little bit more complex than the other resource managers. It is very good for microservices based architecture, containerized Spark jobs, and cloud native environments. It works really well. So we can use Spark on Kubernetes for cloud native or containerized workloads. There is something called Helm charts or Spark operator for easier deployment. We can use these for deployments and job submissions in case of Kubernetes. Kubernetes' most salient features are it provides auto scaling, fault tolerance, namespace isolation, and security. And we can deploy it on EKS, AKS, Azure Kubernetes Service, on any of the clouds. Only thing is we need to have it has a little bit of steep learning curve. It can have a cold start time. Okay, that can happen because we are talking about different pods being set up for Kubernetes. So if there is some wait time, idle time, it will again start up and there will be a cold start time. Then we have to do some kind of resource tuning to avoid any out of memory errors. It needs some bit of knowledge and learning to configure and run it properly. It can be really good for having scalable cloud native or container first data pipelines. And it is good for DevOps centric teams also. It is well managed. So these are the 4 types of cluster managers that we can operate with, and we briefly spoke about what all things to consider while looking at the cluster selection. I hope this video gives you a starting point to think about how to design your cluster, and I hope to see you in more interesting videos in future. So please like, share and subscribe to the channel, and keep listening. Thank you.